Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm delighted that Jacob Czakareski has been able to come back to MSR. He almost didn't make it. His flight was canceled yesterday, and he crawled in at 3 in the morning today. Jacob was an intern here many more years ago than I care to convey. He got his master's and PhD degrees at Worcester Polytechnic, Rice, and Stanford. And besides Microsoft, he was an intern at HP Labs, and he's had full-time positions at Vidyo and EPFL, and now as a professor at the University of Alabama. He's got very wide interests, from wireless communication to social networking, and today he'll talk to us about multi-camera networks. Jacob.
Thank you, Phil. Thank you for the nice introduction. It's a really big pleasure for me to be here. I would say that my whole career started with my internship here, and I'm very grateful to Phil for that. So I always felt like home coming back here, and I really enjoyed being in an environment where you can be so productive and interact with people from so many different backgrounds. So since Phil introduced me well, I will skip this slide. And I have a slide on my interests, which span graph-based signal processing, immersive communication, meaning like visual communication with video signals captured from multiple viewpoints. And I do a lot of stuff related to computer networking, related to data centers and network coding. And I will be very happy to talk to you on all these topics if you're interested. How many people are doing computer networking here? Probably no one, right? Okay. So an acknowledgement is due at this point. The work that I will be presenting was supported by the career award that I won in Switzerland when I was there, from their NSF. And an acknowledgement is also due to my collaborators who helped make it happen. And last but certainly not least, as I said, to Phil Chow, because my career really changed dramatically after I did my internship here with him, and he has always been there, like providing like really good feedback and advice whenever I needed it. So thank you sincerely. Now, what is immersive communication? Immersive communication is, as I briefly said, the act of communicating visual information captured from different perspectives simultaneously. It has a number of applications in remote control, entertainment, and so forth. The two major points of interest that arise there is how do you reconstruct efficiently a viewpoint from where you actually don't have a physical camera installed based on the captured signals. And another one is how to efficiently communicate this information to a client that interacts with the scene. And in addition to a variety of applications, this whole field has like a more broader societal impact, I would say, because it could lead to advances in energy conservation. For instance, people could telecommute rather than work at the office. And that would save, I think, according to the Department of Energy, up to 25% of greenhouse gas emissions. It could lead to improvements in quality of life and also to advances in the global economy. And the National Academy of Engineering lists it as one of the 14 grand challenges of the 21st century. So in terms of like a high-level overview of a multi-camera system, there are three stages that one could delineate. One is capturing the content and encoding the content, then transmitting the content, and then finally how the content is reconstructed at the client. And what typically happens in such interactive environments, there is a client who interactively switches from one viewpoint to another. And then the server would either send a whole set of captured data points, viewpoints, and then the client basically selects the desired viewpoint from its local buffer, or the server may only send those viewpoints that are necessary to reconstruct a virtual viewpoint that the client is interested in. And that is illustrated here, where a client requests a viewpoint new, which is in between. We don't have a laser pointer, right? So in essence, the client requests a viewpoint new, which sits I always think that I'm attached to the computer. So it requests a viewpoint nu that is in between the two actual viewpoints that are captured. And then the server actually sends those two reference viewpoints called right view and left view. And then the client uses that to synthesize it as these virtual viewpoints. Or it could display both of them on a stereo display. Now, the way this virtual view synthesis is done is via depth image-based rendering, and I imagine many people here are familiar with it. The way it happens is that for each capture viewpoint, there is a video signal and a depth signal, and the depth signal basically describes the distances of different objects in the scene from the camera. And then using a procedure called 3D warping, these reference viewpoints, these reference signals, meaning the video signal, is warped to the virtual camera viewpoint perspective. And since we have two reference viewpoints that are warped to this virtual viewpoint, then we need to blend them. And there are procedures to do that. So just an illustration, how do these signals look like? The video signals looks like an irregular image, and then the depth signal looks like a low-pass filter version of it, where there is a single intensity value assigned to all objects that are from the same distance from the camera. So these signals could be either estimated from the reference signals, video signals, using stereo matching, or they could be also captured by time-of-flight sensors. So the specific scenario that I will consider as part of this presentation in the rest of the talk is as follows. We have a set of cameras capturing a viewpoint, capturing a 3D scene of interest. And there is a client that is interested in interacting with the scene dynamically. Now, there is an intermediate compression step that is involved before the content is actually sent to the other end. And these are like the viewpoints that the client can reconstruct. Now, the sender may decide, instead of encoding all captured viewpoints, it may decide to encode only a subset of the viewpoints if the sender thinks that only a subset of them would be sufficient to provide good reconstruction quality of any viewpoint within V1 and Vn. Oh, I'm so stupid. I'm sorry. I'm really sorry. OK, so we have a range of continuous range of viewpoints starting from V1 to Vn, in which nu could be. Okay. Now, the specific setup may involve transport bandwidth constraints, where the network bandwidth may be unknown at streaming time, and also may be limited at time varying. Okay. And also, there may not be feedback from the user to begin with. And our goal would be to maximize reconstruction quality of the content for any possible viewpoint that the viewer may select to reconstruct. So one typical and very good solution that people have approached in situations of similar nature is to do scalable coding. So scalable coding of content, in particular video, is convenient because it automatically adapts, like to the network conditions. If the network conditions are better, you could send more. If the network conditions are not that good, you could send less. And then the reconstruction quality of the content at the client scales with how much data it receives. So it's optimal also in that sense, meaning like you could reconstruct the content in multiple rates, depending on how much bandwidth you have between the sender and the receiver. And people have looked at various like codecs in the past, like JPEG 2000 and H.264 SVC, where scalability has been introduced. Are people familiar with the concept of scalability? OK, that's good. So our take on scalability in this case is to provide joint view and rate scalability. So what does this mean? Let's say we have a set of cameras that we want to encode. And then at compression, at any point where we want to encode more content, we could add an additional chunk of rate called delta R to the new data that is being encoded. And as an output, we create a binary stream, like that is sent to the client. Now, we could do two things when we encode this next subsequent chunk of data called via delta R. We could either refine the subset of views that are already encoded in the bitstream, meaning we have already encoded some viewpoints video signals associated with these captured viewpoints. There's a lot of terminology, so please forgive me if I make an error there. And we could add this increment of rate delta R to improve their quality, meaning if you add more data rate, their video quality of when they're reconstructed will improve. Or what we could do instead, we will not refine the already encoded viewpoints in the bitstream, but we could insert another viewpoint that has not been encoded by then. Okay, so we have like two axes of scalability, view or rate refinement. So the framework that we use comprises three components. The first one is a multi-view video encoder that we apply to the video and depth signals that are captured. Okay, and then we use depth image-based rendering, like to synthesize views that the user is interested but that are not captured. And we have an optimization procedure which would basically decide whether we code a new viewpoint, meaning insert a new viewpoint in the stream. We refine the existing viewpoints that are already encoded, or we interpolate, meaning we don't decide to insert a viewpoint at all. So in terms of coding the video, what we use is a shape adaptive wavelet transform. And it is adaptive because it adapts the wavelet filtering to the object boundaries in the image. So that will allow us to avoid high magnitude coefficients that would arise if you apply the wavelet transform across object boundaries, across edges in essence. Now once we have that, we apply set partitioning in hierarchical trees, which is another algorithm, so that the resulting bitstream exhibits this fine rate granularity. If you have any related questions, you can always stop me along the way. I'll be happy to answer your questions. Now for view prediction and interpolation, we use a 3D warping algorithm that has been proposed somewhere else. And in order to avoid background pixels overwriting foreground pixels, we maintain a depth buffer. Meaning when we do the warping, like different objects in the scene that are projected to the virtual viewpoint may lie on different depths. So we choose the one that is the closest. And then we do this weighted blending of projected views according to the distance to the synthesized view location. And I will explain that in a moment. So here's how the problem looks like if we start describing informally. We have a set of captured views. And then we denote by capital nu sub v sub naught as a subset of the encoded as a subset of viewpoints that we choose to encode. Okay, now since each viewpoint comprises texture, a video signal, and depth signal, we'll need to assign encoding rates to each one of them. And our end result will be a compressed bitstream phi. So what we need to do is to figure out how good each of these viewpoints will be for the reconstruction of a general virtual viewpoint. We need to figure out what's the reconstruction error for a viewpoint given a bit stream. And that's this quantity that I will refer to. Yes, please.
Does this assume that the existing viewpoints are stationary, or can it adapt when they move?
It can adapt if they move. It can adapt. But in the first setup here, we assume that they're stationary. Yes, I don't see a reason why it cannot be applied when they adapt, when they change location. Now the quantity that we will, since we don't know what viewpoint the user may select in the end, what we are interested in looking at is the aggregate distortion, meaning the viewer can pick any viewpoint between Vn and V1. What's the total reconstruction error that the viewer may observe? Now, in order to go about it, to figure out what is this, we have developed in another work a model that basically quantifies the reconstruction error for a virtual viewpoint given an encoded bit stream as a function of the two nearest reference viewpoints, meaning those signals that we capture, and as a function of the location, of basically where relatively this viewpoint is compared to the two reference viewpoints, where x basically characterizes how close it is to one or the other reference viewpoint. And I'll show you how the model works. Here I'm on the x-axis. I show that the relative location of the virtual viewpoint. 0 meaning is aligned completely with the left reference. 1 meaning it's completely aligned with the right one. And on the y-axis, I show the reconstruction mean square error. And this is the Middlebury data set. So the red graph shows our cubic model, and the blue graph shows the sampled values. So we could see that we have a really good match between the actual values and the predicted values by the model. Now, what is nice about having a model, then we could actually include it into an optimization framework where we could decide, how the rate allocation should be performed. Okay. So additional things to consider within this setup is we say we have a certain network bandwidth, which is constrained between R min and R max, and we can set up a parameter called the rate granularity level, delta R. So based on that, we could figure out how many layers of scalability we could have. And then for every layer that we need to additionally encode within the bitstream, there are a few variables that we'll assign. One is what are the encoded captured views by that point that are present in the bitstream. And rate vector basically denotes how much rate we have assigned to each of these captured viewpoints by that point. And then the view vector comprises then what were the viewpoints that are present in the bitstream at every new subsequent layer. Okay, so this is a vector, and it's a collection basically of these quantities. And since our procedure is embedded, these sets also are embedded, meaning naturally, if on the beginning we included viewpoints 3 and 6, this subsequent set will include viewpoints 3 and 6 and maybe something more there. Or it's exactly what I said there. So then using our aggregate distortion formula, we could compute, like what's the aggregate or the total distortion that is observed at the client, given the rate allocation and given the selection of viewpoints to be encoded up to layer L. So typically what we would like to have when we code things in a scalable way, oh, sorry, I don't know why this appeared here, okay. Oops, I think I flipped one slide further, I apologize for that. So we would like to we would like to minimize across the rate vector and the viewpoint selection vector the aggregate rate summed up to layer L, such that at every subsequent point of adding a new layer, that rate doesn't exceed this constraint, where this constraint says like whatever we have added up to that point, it should not be greater than R min, which is the minimum rate that we start with, plus all these L-1 delta R increments. Meaning every new layer, should not exceed, like this value of delta R. So using our old friend, the Lagrange multiplier method, we could transform this problem into an unconstrained optimization where we would use Lagrangian multipliers to include this constraint within the objective function. And what that allows us, we could then reformulate this aggregate distortion as a distortion depending as a sum of incremental distortion that are or reductions in distortions that are introduced whenever a new layer is added. Okay? So with a little bit more math, if we set R min to be delta R, and there is no reason why we cannot do that, we could reformulate the problem as follows. And then we could group everything into one big Lagrange term, which depends on this delta F and the rate assignments. Where now we have introduced different Lagrange multipliers that are indexed by L and K, and they're dependent on the original Lagrange multipliers. Would there be any questions at this point? Yes, Phil.
Just trying to check whether I'm understanding what's going on.
Yes.
So you're trying to, so you have these different rates, and you have a set of cameras, and you're trying to determine for each rate, there's L bit rates, how many bits to allocate to each camera, and how
and which cameras to select to encode.
Okay.
So you do two things. Because remember now we could be scalable and do two, let's say, orthogonal axes. First is like what viewpoints do you select to encode, and how much data rate do you allocate to each encoded viewpoint.
So I guess in the script, V naught is the set
Yes.
of cameras.
Yes,
to encode.
exactly.
And R sub R okay, that thing is
R sub L means
is a
like
vector of rates for each of the cameras.
exactly
That you
that I encode. Yes, yes. There is a lot of notation. I apologize for that. So that's why I would like you to ask, to feel free to ask questions whenever they arise.
And you're trying to optimize, like given some delta R. Now there's an existing state, and you're given some additional bits, and you're trying to see how the delta R will be distributed.
How I
across
distribute the
different-
delta R's, exactly. Do I distribute the delta R's to views that are already encoded? Or do I say, okay, fetch another non-encoded viewpoints, you know, like, and introduce it into the bit stream?
Or do a combination of both. Part of the delta R goes to a new view, and then
No, delta R could only be used for either like encoding new view or like, or you know, like refining existing views.
refining one of the existing views.
Yes, yes. And you know, like you could break down this like into such a small delta R, so you could like basically separate the two decisions. So solving this like jointly is a very complex problem, as you can imagine. And what we resort to is a greedy optimization where we say like if we fix all our prior decisions up to layer L, we could then compute what would the optimal decision be for encoding the next subsequent layer L plus 1. Okay, because doing this over across layers, you know, like it's really complex. And yes.
That's exactly that's strange, because if your delta is small, then to encode a new layer, you're not gonna get anything if you have just a small thing. So you're never gonna start encoding a new layer if you set your delta too small.
Well,
Otherwise you consider several steps.
right. So I mean, it's not like a tiny small. You know, delta. You know, like there's certain impact on delta, but like in the paper we actually look at like a range of values. You know, like where you know like the delta could make an impact on how the optimization works, and there is a flat region over which you know like it's safe to choose this delta value. And I will show you actually that's a good point. So what is interesting also now, so keep in mind that you know like I could start now from layer 0, compute the optimal decision, and then you know go to layer L plus 1, compute the optimal decision, and so forth, given the previous decisions. So what we could do, even like you know like the computation complexity is still manageable, we could go for 2 layers and compute them jointly, given previous decisions. And we observe that this is better because like we now have video and depth signals. So what the optimization, if you are constrained to adding just 1 layer at a time, the optimization may rarely decide to encode new viewpoint, because what it wants to do is add, you know, typically like a video enhancement rate and the depth enhancement rate simultaneously. So if you do these things jointly, like with 2 subsequent layers together, you know, like that problem goes away. And what we do in effect, as I denoted here in blue, we actually compute the current and the subsequent layer jointly. We could still do that. But computing all of them together, it's impossible. Yes?
We can do the opposite. Instead of adding layers, you could remove layers. Right?
Yes,
So
that's
you
true.
get, like starting at the most
That's true.
likely layer.
That's true.
Then go.
You could like, you know, encode all the way to the end and then maybe start, you know, throwing layers. You know, that would be another greedy approach. Yes. You know, which would be the, let's say, the least destructive layer, or like, yes, which would be the least destructive, you know, like either rate increment to being refining encoded view, or like a viewpoint to be removed. You can also do that.
How does your distortion change with the depth precision in this model?
How does it change with the distortion?
So, for example, I mean, the depth is not needed if I'm exactly looking at a view that I'm interested in.
Right.
If that view is coded and if I want the exact same view angle, then I don't need the depth information. So even if we didn't code the depth, the distortion on that would be only the compression distortion, basically.
Well, the thing is, like, since we are looking at coding both depth and distortion, you know, like they both have impacts, you know, like how viewpoints are reconstructed. So, like what we observed that in some points, at some stages, the optimization actually decides to throw in a new depth signal first, before introducing new video signal first, because it, like realized that, adding this new depth value there, it's beneficial.
But how was that incorporated in the distortion function? So when you do the interpolation, I might have missed that.
Yeah, sure, no problem. We have this model which basically like computes what's the reconstruction distortion as a function of this distortion of the two reference viewpoints.
Right, but you also need the distortion for the one viewpoint and the other viewpoint. You also need the quality of depth information.
That is in the distortion. Yes.
It's not just color distortion.
Yes, it's both. It's both. Yes. Thank you for the question. So where did I stop? Okay. So the way our algorithm works then to run this, we initialize this set v sub naught, and we initialize with the two like furthest most reference viewpoints, and we set a value to delta r. And then we set like all the assigned rates up to that point to be 0. And since we just have two viewpoints included in the bitstream, we just have 4 values there. And we start with the index L, meaning this will be the first layer. And then we iterate as long as like L is less than capital L. What we could do, we choose from one of these two options, refine, meaning pick one of the viewpoints that are already encoded, either image or depth, assign an additional delta R to it, or we could insert V, where V is one of the viewpoints that have not been encoded yet. And again, we could insert image or depth. And the action is the one that selects that leads to the smallest incremental distortion. And then we increment L and we run this like until we are done. So this is just an illustration how the algorithm works. So these bars, the vertical bars, the white bars, basically denote like how much rate we allocate to each viewpoint. And then the axis here, R, basically denotes the progression of rates, as the rate increases. So let's say we start, and we choose where we need to throw in this delta R. So it could be in any of these bars, so to speak. So for instance, here we assign it to V2. And then at the next rate increment, this one goes to V1. At the next rate increment, this goes again to V1, and so forth. This is just a graphical illustration how the optimization works. Now, then we said, like, how about we go one step forward? How about if we know actually something about the user in terms of its actions? And, we could even like try to speculate, like what views the user is interested in selecting. Can we combine this with our optimization? So in order to do that, like first we said, okay, let's go, first quantize this space of viewpoints that the user can select. And we generate a discrete set V bar, okay, which is bigger than the set of captured viewpoints. And then we say, as a first try, let's see, like if we can model the user actions as a Markov chain on this set V bar. So accordingly, we could assign a transition matrix that would basically describe the probabilities of the user selecting different viewpoints, given like where the user is at that point of time in the viewpoint space. And this has like analogies, with what people have observed, for instance, in IPTV channel switching, how users flip between different channels. This kind of modeling. So what will such a model allows us? First of all, if we could anticipate the user's actions, we could reduce the application latency, meaning we could send or encode only those viewpoints where we expect the user may be selecting from. And also it could enhance coding efficiency, meaning if we don't expect the user to be checking certain viewpoints, we may not include them into the optimization at all and not spend bits there. So the way the formulation then proceeds, we have a horizon of the user actions, or which we say we will speculate what views the user may be selecting. And then given like a viewpoint I that the user selected at time ti, we could define a state in this Markov state space, which is basically determined by the set of viewpoints that the user selected up to that point. And then using our transition matrix, we could describe the probability of that state. how likely it is if the user samples viewpoints across this horizon, it ends in a certain state. Starting from an initial state, we say like at some point maybe we receive feedback from the user and we know where the user has been at that point. So then we could use this approach to compute the aggregate expected distortion that can be associated with the user interacting with the scene, where like we multiply these probabilities of the user being in each state times the cumulative distortion that accounts for all the viewpoints that the user experience along that trajectory. So then what we would like to do is basically say we would like to minimize this distortion of the whole horizon that we are looking at, such that the rate that we send to the user at any point of time doesn't exceed the channel capacity. In this case, the capacity of the channel may be the user's downlink bandwidth. The nice thing about this is the objective function is actually separable. So we could find these allocations of rate across all layers that we may encode for every time instance separately. And then another thing is that typically like these user actions may lead to very sparse matrices P, simply because they are like viewpoints that they select may be concentrated within a narrow range. So that makes computing things easier. So rather than summing over all views, we could only select we could only sum over a smaller set of views that we believe the user may select from as time propagates. So another interesting point to note is that if we have, let's say, a frequency at which the user may send feedback to us saying, okay, I have selected this viewpoint, and then after some time we select another feedback saying I'm at this point, we could study through such a framework the impact of this frequency of receiving feedback from the user. Meaning if this h is 0, meaning the horizon width is 0, that means we know the user actions at every ti. And then if h is infinity, we basically go back to that first model where the server receives no feedback. So we could see like how the optimization scales as the frequency at which we could hear from the user changes. So going now to experiments that I would like to show you, the results from experiments that I would like to show that illustrate the efficiency of our methods. We will examine the coding efficiency when we apply our framework to multi-view image data as well as to multi-view video sequences. And we'll use two reference schemes. The first one basically says I will do uniform allocation across all captured viewpoints. And then I will encode it and see what's the reconstruction quality of the user. Meaning each of the viewpoints is treated equally. And then I'll use another method called H.264 SVC. It basically uses the latest scalable video coding extension of the H.264 standard to code across views independently at every time instance, so that the user can switch at every viewpoint basically to allow random access to the user. So in terms of multi-view image data sets, I will use these sets that are shown here, Rocks and Middlebury, that people have typically used in experiments. And the resolutions are given here, and they comprise 5 captured viewpoints. And then for the video data sets, we'll use data sets that have been captured here at Microsoft many years ago. And they're Breakdancer and Ballet, and they feature 8 camera viewpoints, and the frames are captured at 15 frames per second frequency. So further details about the experimental setup, we basically assume that for the Markov model that we studied, there could be 3 virtual viewpoints between every pair of captured viewpoints. And the way we measure video quality is as the luminance mean square error. Now for the captured viewpoints, remember the user may also select capture viewpoints. And then we could measure what's the reconstruction error, because we have a reference signal. Now how do we go about measuring reconstruction error for an interpolated view. And the way we do that, we basically synthesize that interpolated view using the original non-coded signals, meaning using the original signals for the two reference views. And then we compare that to the to reconstructing that viewpoint from encoded versions of those signals. And then we, in terms of view selection models, we use two models. One is a balanced one, meaning like if a user is sitting at a viewpoint at some point of time, with probability 0.5, the user may stay in that same viewpoint. And with probability 0.25, it may switch to the left or to the right of where the user is sitting. And the unbalanced one is like basically pushing the user into selecting one of the views to the left, preferentially with much higher probability. And when we explore the impact of user feedback, we say that for image data, we say that the user, can send feedback to us every 5 time slots. And for video, we extend that to 50 frame intervals. So now the graph is like really complex here, so I'll give my best to explain it to you. On the x-axis, I show rate in bits per pixels, and on the y-axis, I show PSNR. And this is for the coding efficiency for the dataset ROC. So remember, we are talking about image data now. Another thing to keep in mind, we are dealing with the balanced view switching model that I introduced. Now, the different graphs, what they represent is measuring video quality as a function of how much encoding rate we can spend at every time instance, like as time evolves. Remember, the feedback that we could receive from a user is five slots. So we have time instances from 0 to 4 at which we measure video quality, and they're described by different colors. And in this case, we compare the adaptive approach. Yes?
You didn't talk about in video. Do you do any motion prediction across frames?
I will come to that. I will come to that.
This is all
Yes, these are all images. These are all images. Now, so the two things that we compare, the adaptive approach, meaning we say we know this probability of how a user selects views, and the non-adaptive approach where we say we'll use our optimization, but we say we don't know anything about the user, meaning that each of the viewpoints is selected uniformly. And one thing to notice is that knowing these view preferences associated with the user can help a lot in terms of coding efficiency. So you could see, for instance, that this black curve here denotes video quality at time points T1 and T2 for uniform P. And this one here denotes the same video quality for non-uniform P. And then we could also see differences in terms of whether we measure video quality for captured viewpoints or for synthesized viewpoints, which also makes sense simply because of the fact that for the captured viewpoints, we don't do any synthesis, so their video quality will respectively be higher, as is illustrated by this red graph here with the boxes compared to this magenta curve. Yes?
Sorry to be so slow.
No, please. I mean, there are so many parameters also. So,
the time, for example.
Yes.
So these are two different, let's say you have T1 and T equals 1 and T equals 2. What does that mean?
Exactly. So let's say time 0, like I receive feedback from the user, I selected viewpoint v is equal to 4. Okay? And then at time slot t is equal to 1, we don't know where the user could be. Okay?
Because your horizon is 5. You're
Yes.
going to know every 5.
Exactly. So then at time instance v is equal to 1, we basically say, if I sweep the rate axis, how much rate I allocate, okay, and measure video quality at the client, this is what kind of curve I will obtain. And then at time is equal to 2, I do the same thing. Time is equal to 3, time is equal to 4, time is equal to 5. And there are also two other parameters that come into play. I could do that for uniform P, where the user could pick any viewpoint along this range of viewpoints that it could select, or I could select this adaptive. I would know what the user said. I will have a model of what the user may likely be to select. And if I, like use that, in the optimization algorithm, there will be different rate allocations compared to the uniform case, right? So I'll have like two graphs for that as well. Does it make sense?
So far, but like
Yes.
you're showing one rate graph.
Yes.
So when you say t, it's a curve for t equals 1 and t equals 2. That means
Right.
it's the same curve for both t
Yes.
equals 1 and
Yes. Yes. Yes.
Okay.
Yes.
And v equals 4 means the user was at v4
Yes.
at time 0?
Yes. No, so what v equal to 4 means like, rather than showing you like an aggregate over all views, what this shows is like we pick one viewpoint, and then we measure video quality that the user may observe at that viewpoint for that particular time index. So that's why I said there are so many parameters. I apologize for that. So when I say v is 4.25, that means I'm dealing with a virtual viewpoint, because we index the capture viewpoints with integers, and we index the virtual viewpoints with non-integers, meaning like between 4 and 5, I could have 4.25, 4.5, and 4.75. And those are the...
Between 4 and 5.
Excuse me?
It's 1/4 of the way between.
Yes, yes, exactly. So between 4 and 5, I have three virtual viewpoints, and then I could measure their video quality at any point of time. There are like a number of parameters that come into play, and maybe this was not the most ideal way of representing them. I mean, in the paper, at least you can see all this information and then read it at the same time. Yes, Dine?
If you're measuring always at the view 4, for example,
Yes.
then what you're doing Monte Carlo on what was on the original, the last information that the viewer sent.
I could measure it anywhere. I mean, these are just like a few viewpoints that I included here. I could measure it anywhere. I could measure it at viewpoint 0.25, 1, 2, and so forth. Yes.
For the red square, you're saying,
Yes.
I'm measuring at T2, view 4, adaptive scheme.
Yes.
But the last time you received information about the...
Was at T0.
Was looking at.
Yes.
Was at T0.
Yes, exactly.
What did you receive at T0?
I received the information saying at this T0 I have selected, I have to look at the paper. Maybe I selected viewpoint 4 or 3.5, I'm not sure, I have to look it up. So this basically shows at viewpoint 4, what would be the video quality if the user selected at viewpoint 4 at time t. T is equal to 2, I'm sorry. Basically, I'm giving you what view...
The result's going to be very different if at T0 he was already at V4, or if T0 he was at
Yes,
V1.
sure,
The
sure.
result's going to be very different.
Yes, that is true, that is true, that is true. But what I'm showing here, for a given viewpoint that the user selected at 0, how video quality would evolve, if I use the uniform or the adaptive model. Yes, what the user selected, it makes certainly a difference. But there are so many parameters here too, so it's really hard to combine everything. And I don't know how meaningful it will be then to just let me finish the point, to maybe show an aggregate distortion of all the views, because we talked about this with my co-authors. Basically, sum all the views and they maybe show there. Maybe we could have done that. I think maybe I have a graph later on that shows it when I try to talk about motion compensation. But there are a lot of parameters into play. But I hope the setup is understandable by now. The user selects something at T0, and then its actions evolve over time. And every time point, every subsequent time, I say from the range of views that the user may view, what typical video qualities the user may observe as a function of how much data rate I can assign to the bit stream. Maybe, I don't know, having 3D or 4D graph, may help.
Yeah, I think you might have alluded to that in the last statement that you made. So the graph, the x-axis then is basically if you were to run the experiment over and over again with different rates of allocation, with
Yes.
different delta R
Exactly.
at each time, that would be the point. So if you were to do a delta R with only 0.2 at each instant, that slice would be what I would observe.
No, so to correct you, and I apologize, I'm not trying to be rude. Did you finish your statement?
Yeah, I'm trying to understand.
This is the total rate. That's why I was jumping ahead. This is the total rate.
That's the total rate.
The
So
total
then
rate.
what does it mean to say, I'm trying to say, see, at time instant t equal to 0 for view 4, I wouldn't expect a graph. I would expect a single point. What does the graph mean? So at time instant t equal to 0, v equal to 4, depending on your settings, there will be a fixed rate associated at
Yes.
that time.
Yes.
in that case, then what is the x-axis representing?
The x-axis represents what is that rate. The rate could take different values, the total rate, right?
So you're running the experiment multiple times for different rate values, and that's the.
This is the the total length of the bit stream.
Right.
The bit stream may be like 0.6 bit per pixels. Maybe it could be like 1.2, 1.4, and so forth.
But that allocation depends on how you allocated the rate for a single experiment. So the total rate could be 1.5.
Yes.
But at some point you may not have allocated the entire thing, right? So at t equal to 0, maybe you only allocated for that only 0.5.
Can you clarify that? Like what?
This is image, right? The way I understand it is, in the beginning you haven't allocated all the bits needed for the picture.
In the beginning, I haven't allocated anything. And then I say, as increment is L, delta L, 2 times delta L, 3 times delta L, and so forth. I may choose to refine or insert new viewpoints. And in the end, I may end up with a bit stream that is long, let's say 10 megabytes. So then I compute, what are the equivalent rate in bits per pixel, and then I show that on the x-axis. This is not delta R. This is the total rate.
Probably not delta R, but at t equal to 0, do you expect the curve to be? I'm still failing to see.
So at t equal to 0, the video quality may be different, right? I may allocate 5 megabits per second, I may allocate 10 megabits per second, I may allocate 20 megabits per second to the total bit stream, right?
Right.
Remember, T and delta R are orthogonal things. It's not that I start at time T and I say I assign delta R and then I go to 2 times T and I assign 2 times delta R. They're two independent things. T describes the evolution of the user over time. He's like sitting in a Markov chain and says, I will go to select this viewpoint with this probability, I will go to select this viewpoint with this probability, and so forth. Now delta R, is orthogonal, meaning like, your bit stream, increases by delta R, up to, this value, irrespective of time.
Okay, I think that would make sense from a video point of view, but from an image point of view, once you have transmitted some data, then that data is already there, it's not changing. And all you can do is to continue adding more data as time progresses, basically. And since this is an image example, that's where I'm trying to, if you had, let's say at t equal to 0, if you had transmitted everything, let's say you had infinite bit rate at t equal to 0, transmitted everything, then later stages of evolution, you don't have anything more to send. And the graph would, in that case, would be a flat line. Is that a correct understanding?
Yes, we have spent a lot of thought about that, so maybe we could discuss it offline, because it may be that the content changes itself, and also another thing that we considered is that even though it's images, it was hard to incorporate that feature in how the compressed bit stream is created, to have that scalability as well. Given that what is at the user, can you encode something further so that still you maintain this scalability? But we can talk about that offline. Yes, we had that consideration in mind. Yes, sir.
Talk about the bump there on the black T1, T2 line. T1, the black line with pluses.
Bits per pixel, there is that bump on the black line.
Yeah, it just jumps.
Here, yeah, that's a good point.
Why? Usually the RT curves are roughly convex, right? And that's one that jumps out from.
That's true.
It's probably saturated one of the views, and then you don't have enough bits to transmit enough.
I suspect that's what happened.
You don't use it because
until a point where it makes a difference, and then it
Yes,
goes up.
yes.
So, the rate seems low. The quality seems low for the rate, so it's like half a bit per pixel, you got 28.
Yeah, black is not.
I have to see what the equivalent number is in total, that you're spending for the data set. Maybe it's in the paper, right? We can look it up. Any other questions? Thank you for all the interaction. I really appreciate it. So I have a similar set of results for the unbalanced view switching model, where now, the user has a certain preference for switching, let's say, to the left compared to staying in the same view or going to the right. But in general, we observe the, we observe the same, let's say, differences between knowing the user action, knowing this adaptive transition probability model and the uniform P. And again, the same difference between, video quality observed, when the user selects a capture viewpoint compared to when the user selects an interpolative viewpoint. Now, switching to video data, here are some results for breakdancer. And again, we are going back to the balanced view switching model. So the three systems that we compare is ours. I know the probability distribution of view preferences selected by the user, a uniform P model, and H.264 SVC. So what I show here on the axis is total rate, but now it's not bits per pixels, but rather like a total bit rate is megabits per second. On the y-axis, I show the average distortion. Okay? And again, if we had like a lot of discussions with our with my co-authors, what to show on such a graph, you could think of multiple perspectives. So you could, like see all the possible trajectories that a user may select and find the average. And what we have shown here, I think, is the average distortion that a user experiences along a typical trajectory. Meaning, like we looked at, how the user selects different viewpoints along time, and then we, computed what is the average video quality or the average distortion that the user will experience along that trajectory. And that is a function, of course, of how much data rate we can send. So that's what we show on the y and the x-axis. And we could see that, like not knowing anything about the user, like leads to the worst performance. Now H.264 is in between. And we could see that our approach outperforms the two.
About the user is the same optimization without having any any idea of
exactly what the user does. Exactly.
And how does the user select a viewpoint?
The user selects this a viewpoint according to this model. The user is in a selected viewpoint, and it says with probability 0.5, like at time instance t plus 1, I may select in the same viewpoint, and with 0.25, I may switch left or right.
Assume that you know that model, you assume that the user is following that model.
Yes.
What if the user does not follow?
Probably I don't have that here included in the slides, but we did also like some analysis of that. That's a good point. Yes, Cha.
So the H.264 effectively also sort of following the uniform distribution of the user. And so the gap between H.264 and the red curve is because of your ineffectiveness of scalable coding, or?
Well, the thing is, like, here's what H.264 does. It takes all the captured viewpoints, and it codes them predictively as it would encode video, but across space, not time. And that's what it does. So it encodes all of them. Now, in our approach, like, we may choose not to encode all of the views. And then we may choose not to assign the same data rates to each of the encoded views.
But if P is uniform, why would you not encode all the views?
Well, because like you could still use like the captured viewpoints to interpolate other viewpoints. Like you may still like get some benefits by like throwing away captured viewpoint and then just reconstructing it from a non-captured viewpoint.
And so why is the gap between the H.264 and the uniform P case?
Well, in this case, like the recall that here the uniform allocation is basically allocating equal data rate to each of the views, and that's what it encodes.
No prediction across views.
No. So it treats all the views equally here. Whereas here, like we apply our optimization, like and take advantage of what the user may select. Yes?
Why is H.264 measured from 4 to 15 bit rate, and everyone else was measured?
Yes, that's a good point. Well, the thing is, like the way the codec is configured, we explained that in the paper. We use 6 MGS layers. So they have like like predefined, like configurations, how many layers you can encode, and like how many temporal and like rate layers you could have, and that's what the codec provided. It's not as fine rate as ours.
So I guess the main difference, even in the blue curve, you're not using any prediction between views in the coding.
We do.
Prediction spatially between views in the compression.
We do, yes.
And in the red curve also there is prediction across views spatially.
Here, what we do, we encode all views, but using uniform rate allocation.
Uniform rate allocation, but does it use prediction across views spatially? Does one view predict from the?
Yes. That's a good point. I think we do.
Still you use uniform allocation for the views, though there is predictive coding between views?
Actually, let me take that back, because I think like we did like a number of let's say uniform systems, and I think this is like the most reference one where you can think of where each of the views is encoded independently, assigning the same data rate to each viewpoint, and they're encoded H.264, with no spatial prediction. I can look it up in the TIP paper,
That makes sense, because with no spatial prediction, I would expect the two graphs to go.
Yes. I think this is the simplest one, the uniform reference that we could think of. And I have another graph where it shows, where all these gains come from. And are there any other questions? So here's another graph that basically illustrates the temporal evolution of video quality. So I've shown you a graph where we saw video quality versus rate. And now I show you a graph which shows video quality versus time. So again, there are like three colored graphs which basically show the performance of the three reference schemes, ours, the uniform allocation, and H.264 SVC for three encoded data rates. One is 14, the other one is 9.4, and the other one is 4.7. And here is like the, I think I don't, okay, so it's nice. So here we have also labels of one trajectory that the user selected over time. So these numbers here, 4.25, say like at time 0, the user selected a virtual viewpoint index 4.25. Then it went back to 4, then it went to 3.75, 4, 3.75, 3.75, and so forth. And it does this with the temporal frequency that we described. And you could see that, like, for instance, video quality, of course, improves when you add more data rate. But then, depending on where the user is, like whether it selects a captured or an interpolated viewpoint, that quality may vary, which is expected because typically the video quality of an interpolated view is much lower. And, at the bottom, we also show the corresponding curves for SVC. So SVC is actually this dotted line. So we could see that how we also outperform SVC over time. And here below is that uniform approach that I described. Dine, did you have a question? Or someone else was raising his hand? Oh, it was you. Okay, please.
Something that doesn't sound very intuitive is
okay.
That the rates, when you switch from 4 to 375, there's a big loss in PSNR. In 375 to 3.5, now the additional loss is much less. And my intuition says it should be the opposite. 375 is somewhat close to 4. See, when you jump from 375 to 4 to 375, boom, you go down.
Wait, there is no 375, there is 475.
No. The position, the user view selection.
Okay.
See, when you are position 375.
Okay, here.
There.
Yes.
So you had a big dip in PSNR. You go back to 4, the PSNR goes up again
yes.
in many of the curves.
Yes.
And then when you go to 375,
yes.
it goes down a bit.
Yes.
That's expected.
Yes.
But then from 375, when the user 2 steps later goes to 3.5, there is only a small drop. Right? And intuitively, that sounds strange because there's a big drop because I'm interpolating.
Right. And this one is also interpolated. 3.5 is interpolated.
Right. But what I'm thinking is the asymmetry. How much more loss in PSNR in moving from 4 to 375 than it is from 375 to 3.5?
Well, 4 is a captured view, right?
4 is a captured view. 4 is a captured view. And another thing to keep in mind.
Which means that on this one in particular, the interpolation hurts quite a bit.
Yes.
As soon as you switch off even a little bit from the capture view.
Yes. Yes. Yes.
Okay.
The quality drops. You know, like, and it depends on the distance. You know, like.
Sorry, actually.
If your 375 is closer to a reference view, you know, so typically you saw how the curve looks like, error versus distance. You know, in the middle, you know, it's typically the highest.
Yeah, never mind. You're right. It should be
And you also have to, no problem, no problem. You also have to keep in mind that, you know, like, since you also have this frequency of the, you know, feedback receiving, sometimes may even happen that the interpolated view may improve in quality if it's just after we know, you know, what the user selected. Because then we have like a narrow range of views over which we speculate, and then we can improve that same interpolated view quality, you know, just because we are closer in time. You're welcome. So last thing about performance of the framework is basically, as I said, like how do all these like pieces, you know, like contribute in terms of improving performance. So on the x-axis, I show you rate, again, total rate at which we encode. And on the y-axis, I show video quality. The content is breakdance and the balanced view model. So the simplest, most reference is uniform allocation. And we call it simple allocation now. OK, that's here. Now, if we use our optimal allocation, but we say the user model is uniform, then we get bumped up to here. OK. And then here is H.264 SVC in between. And then we have like the full optimal model in the sense, you know, we take advantage also of the user model as well as we run the optimization.
But H.264 does not have a user model, right?
No, no, it doesn't have. I mean, in the encoding process.
So your optimal allocation without a user model loses to H.64 without a user model?
Yes.
Why?
But you know, like in H.264, what we do here, like we encode the views, okay? And in the optimal allocation, we don't take advantage of the user model. We don't take advantage of the user model. Everything is encoded uniformly.
So does H.264, right?
Yes. The reason why we believe that, I think it's maybe even explained in the paper, you know, like here, you know, like the user model is such that the encoding is still not very efficient, you know, like when the user switches according to this model. So knowing the model, you know, like introducing into the improves a lot. And, you know, like H.264 uses all the tools that you can think of, you know, like motion prediction and so forth. So, and we are using a compression algorithm that is
Underlying compression is
yes.
simpler than
It is simpler. We don't use any like of the HVC and SVC models. We are much better in terms of how fine you can be in terms of, you know, rate granularity, but we don't use any of the tools that they have. And I think this last slide would answer what Cha was asking. Then we said, okay, can we actually try to introduce temporal prediction while maintaining, you know, this fine rate, fine grain scalability? And it turns out, depending on like what user model do you use, you know, like that may be beneficial or not. And remember that since we are using the wavelet codec, wavelet codec is actually not very good in encoding over time, because, you know, like these images that you obtain when you try to find the differences between the two viewpoints, you know, like they look very noisy, like, you know, like, so you don't get a lot of benefits when you try to include also time across scale. Unless you try to also estimate motion prediction and so forth. But then the codec becomes very complicated, and in the bitstream, you know, like it's hard to manage. So anyhow, to make the long story short, we looked at two cases. One, we said like if you have the balanced view switching model and the user doesn't switch a lot, and we try to do simple temporal prediction, meaning, you know, like we take the next video frame and then we subtract it from the previous video frame and we encode the differences. On top of what we do, you know, like so far, we could see that with temporal prediction, we do get some gain if we include that into our model. Because recall, you know, like our model encodes things in an embedded way, but it doesn't exploit temporal correlation between video frames of the same viewpoint. So if we add that without doing motion search or anything, in just like simple temporal prediction, we do get some gain, maybe around 1 dB, a little bit less. Okay, but since everything done with a wavelet codec, wavelet codec has been shown that they're not very good in dealing with motion compensation. Now, once we switch to the unbalanced view switching model, meaning that the user switches frequently, we actually get hurt by if you try to introduce a temporal prediction. And the reason being is like when we try to do temporal prediction and then we encode these image differences, like they require so much rate in order to be encoded, you actually become less efficient. And this is illustrated here on the graph, where the black curve shows how much PSNR versus rate I could achieve if I do temporal prediction compared to the case when I don't do temporal prediction. Okay, so this is still like a topic to be investigated. Maybe try to incorporate like more complicated, more motion compensation models, such as those in use in typical video encoders. But then this whole concept of fine-grained scalability, like maybe at a danger, so to speak, because it may not be possible to maintain it. So in conclusion, how much more time do I have? Okay, perfect. I'll wrap up. I wanted to have a few more slides, but then it's not an excuse. My flight got canceled, and I had some other things. I wanted to tell you like how maybe this framework could be used, like to tackle some other problems. So first, to summarize, I have shown you a rate and view scalable multi-view coding framework, which comprise a scalable wavelet-based coder and an optimization algorithm. That, on top of it, also took advantage of a view switching model that may exist about the user view selection actions. And you have observed that it leads to enhanced efficiency and interactivity. Now, this is why I wanted to have an illustration. What could imagine that we could use this model to basically figure out how many cameras do we need to cover certain scenes sufficiently well enough. So there is something called Cisco Stadium Solutions, and what they provide is a framework where you are able to like place a number of cameras, and even Comcast has this, like for sports matches. And then they deliver this to the client, where the client could only switch between the captured viewpoints. So you could think that we could use our own framework there, where we could basically figure out how many cameras do Cisco needs to place, in order to deliver video quality that would not go below certain criteria. And there are other applications where one could imagine using this analysis framework to figure out, how many cameras we could place in a remote monitoring camera sensor networks, and so forth. So some of the things that we've been working on is how to extend this to multicast. So let's say we have like a population of clients that are interacting with the scene. Okay, and then the user, like I said in the stadium solution, you're at a stadium and then you want to flip between views, on your tablet or on your, like, let's say, mobile phone. And then if let's say Cisco, using the stadium solution, wants to broadcast a stream to everyone, such that everyone is able to switch between different viewpoints, how do you do this? And how do you incorporate the fact that some users may have correlated actions, like they're members of the same social network? Another thing that we investigate is how to add on top of it like channel coding methods like FEC and network coding, if let's say this is delivered over wireless environments. And other things that one could consider here is like doing distributed coding methods and so forth. And another issue that we tackled in the presentation is how one could maybe design efficient temporal prediction methods. Now, if you guys don't, are there any other related questions? I wanted to show you something completely non-related and maybe is it okay?
Couple slides.
Yes.
No more.
We are very, very high level, it's just to tackle your brains a little bit. I've been, so this is like, I'm also biased because what I will show you, it involves me, but still like, it's also a bit of a philosophical question for me, how computing has evolved. So in the past, I was not born then, but people said, there was the mainframe and then people would go there and then they do their jobs, and then, like finish their computing and they'll go back home. But then, then there was the era of the personal computer where people, could take their computers home and do the computing there. Now, there was another development that evolved sort of independently, and that was the network. The network appeared in between. And what the network allows us is basically like to use the computer not as a device for computing only, but also for communication. And that would allows us, if my animation is correct, to go back to the mainframe, because now we could do things remotely and basically compute everything in the cloud. So what we would like from the cloud is basically to run everything on the go and to do these things completely in the browser. And a number of possibilities, like one could imagine, like for people who do graphics, and they're somewhere, let's say in Singapore on the airport, and they want to edit an image, and their laptop doesn't have this GPU capabilities and so forth, they could connect remotely and do this. And also what this could allow us is we could basically charge the users for using a software application per use. The user doesn't need to install the application locally and pay for it for life. Maybe one wants to use Microsoft Word for 2 hours and pay for that. And on top of that, what we would like, or what is desirable, if you have your own app, can you embed it in a browser? So when I go to the web page, I click on it, and I want to run Rico's application. So with that, I would like to, so I think that I would like to show you a quick demo that describes, that maybe this is all possible.
It's funny that you mentioned Photoshop, because Photoshop has changed the model where you can't buy Photoshop in the client anymore.
Yeah, exactly. They have this Photoshop Adobe Cloud solution.
My name is Nicola, and I'll give you a quick preview of Mainframe 2,
I hope the audio
which is a new type of cloud that lets you run any software in a browser.
You cannot see it.
What makes Mainframe 2 special is that everything just works.
I thought that would. Why the video doesn't display?
There's nothing to install.
This is unfortunate.
You just click.
Let me try. When the guy was here, we could actually do it. The guy from system support.
Do you see it in your screen, the video?
I cannot see it also, which is really bizarre. I think we changed the resolution and then it disappeared. Let me try to go back to the original resolution. When the person who was helping with the computer was here, I could see it because I played it and we tested the audio.
Actually, why don't I suggest that we
oh, yeah, there it is.
People who are interested can.
Let me try.
On an application you want to use, and it comes up.
Let
All
me
applications behave exactly.
I'm sorry for this.
My name is Nicola, and I'll give you a quick preview of Mainframe 2, which is a new type of cloud that lets you run any software in a browser. What makes Mainframe 2 special is that everything just works. There's nothing to install and download. You just click on an application you want to use, and it comes up. All applications behave exactly as you would expect, because they're exactly the same. Which also means that there are no code changes required if you want to put your application on Mainframe 2. Everything is really snappy. Typing feels natural. Mouse clicks are instant. While we're in private beta, you'll get a real-time response from the Western US. Everything works fine even if you're on the other side of the world. It's just a tiny bit slower. Very soon, we'll be launching servers in many more places. It's easy to bring your own files from a cloud storage, like Box. We use it as a cloud hard drive, which means that your files are never synced to Mainframe 2. They remain secure, so you don't have to worry about someone else accessing them. And since your files are already in the cloud, you don't have to upload them or manually sync to your devices. Your cloud storage already does everything for you. From a Mainframe 2 application, you open a file directly from Box, and then do your work. When done, you just save it back to the cloud. Everything is automatic. In fact, software often runs much better in the cloud than on a local computer. That's because our servers have faster processors, better graphics, more memory, and faster disks than most computers in the world. So hopefully this gives you an idea of how much easier it is to run applications in the cloud and connect from any browser with no plugins required. We're still in private beta, but you can sign up and get early access at www.mainframe2.com. Thanks.
I'm sorry for a little bit of PR, but since I'm involved,
You probably know we're in the business as well.
Yes. One thing to remark about Rico's question, so Adobe has this model, but they then still require you to install a small client on your end when you run this. And ours is completely HTML5. Exactly. And we have signed up a number of customers, but we still have a few licenses for research purposes. So if people who do graphics are interested, I could give you set you up with an account on the website, And then you go there, you can run your things, install apps, and see, how your favorite graphics application works in the cloud. Thank you.